Let's start our new section. 5.1 is about randomness, probability, and simulations. So what is the law of large numbers? The more repetitions of any chance process you do, the proportion of times a specific outcome occurs approaches a single value. So let's say you roll a dice. If you roll a die, it's a 1 in 6 chance you get a 1. The more times you do this, the probability will approach that 1 in 6. So think about theoretical and think about experimental. So the more times that you do the simulation of rolling the die, the closer it'll get to that theoretical. That is the law of large numbers. So let's think about tossing a coin. So, we have heads and you have tails as your option, and it's half and half. Okay. So, proportion of heads. So, the more times you do it, the closer you get to getting your probability, your experimental of half. So, it'll get close to the half mark. So, if you roll it 10 times, you should get close to 5, but definitely not exactly 5. Except whenever you do this many, many times. So let's say you do it 200 tosses. So see how the proportion gets closer to that half? It's close, close, close. There it is. Look, it's right around the half mark, which is our theoretical. So how do we interpret a probability? So it's always between 0 and 1. A probability of 0 means impossible. 1 means guaranteed. It's guaranteed to happen. So what you want to do is you want to look at the long run relative frequency or the predictive relationship in a large number of trials. So over the long run, let's look at the relative frequency. So that's going with the large number of trials. Beware of scientific calculator notations. So this 2.3e to the negative 10 means you move this decimal to the left 3 times. So 1, 2, 3, which gives us 2 zeros in there. So that probability is really close to 0, but it's not exactly 0. So it's never 2.3. You've got to think about what e to the negative 3 means, and you have to convert it. Okay, if the probability of getting a sum of 7 when rolling 2 die is 1 in 6, interpret this value. So you're doing 2 dice, and once you roll the dice, you're going to get 2 numbers, and then you're going to add those together, and we're looking at the probability of getting that sum of 7. So let's interpret what this means. If we roll 2 dice many times, the sum of the dice will be 7 about 1/6 of the time. So remember in chapter 1 how we never said anything was absolute. We use those words roughly, about, approximately. We want to continue using those. Don't say it will be 7 1/6 at a time. You have to add in that word about, approximate, roughly. It's never absolute, remember? So which of the following outcomes from a coin flip 6 times is more probable? So let's look. It says heads, tails, heads, tails, tails, heads. So even though they're kind of like opposite, like alternating a little bit, you still have 1, 2, 3 heads, 1, 2, 3 tails. But every coin flip is independent, and it's also half of the time it'll get you heads, half will get you tails. So the way you determine the probability is you do the probabilities times each other. And so that ends up being 1/2 times 6, or raised to the 6th power. And then actually the same thing happens here because the probability of getting a tails is half, probability of getting a tails is half, probability of getting tails is half, and you get the idea, right? So half times itself 6 times. So they are the exact same probability, equally probable. Because each of these outcomes is independent. Just because I get a heads right now doesn't mean I'm going to get a tails next. They're independent of each other, which we'll talk about in a later section. So what are some myths about randomness? We have three, I think, two or three myths. Law of averages means that the next outcome must be something to balance out the previous. So kind of like what I was talking about, heads, tails, like you would expect it to kind of alternate, but that's not the case. Um, the law of averages means that the next outcome must simply balance out the previous. That's a myth. So the saying, somebody saying, they have three girls, surely the next child will be a boy. That's not how it works. It's half chance it'll be a boy, half chance it'll be a girl. So you can't say just because they have three prior means that the next one will be a boy. I'm sure they hope it will be, but the probability is the same. Probability of getting a girl is half. Probability of getting a boy is half. Okay, the next one. Coins, die, chance processes, etc. have no memory. Things just balance out in the long run only, not with a small number of trials. Be careful applying the law of large numbers to a small set of trials when it only applies to a large set. So you want to make sure you do a large number of trials. If you do a small set, you can't say that it's going to balance out. Okay, so let's go into simulation. What is the purpose of a simulation? It's to estimate a probability when it might be too difficult to calculate theoretically. Okay, so what are the four steps? We have state, ask the question of interest. So what are we interested in finding? Plan, describe random assignment process. State what is to be recorded at the end of each repetition. Do, perform multiple repetitions. And conclude, use results from the simulation to answer the question. So you go back to the original. These are the steps that you'll do each time that you do a simulation. You have to list them out. State, plan, do, conclude. 4 steps. And you must do all 4 steps. It says, do we need to do the 4 steps for each simulation? Yes, sure do. You want to get credit for it? Do them all 4. Okay, so here is an example. So think about in basketball. So if someone's on a streak, that means that they are, once they make one basket, they continue to make the baskets. Then they are said to be streaky. Okay, suppose that a basketball announcer suggests that a certain player is streaky. That is, the announcer believes that if the player makes a shot, then he is more likely to make his next shot. As evidence, he points to a recent game where the player took 30 shots and had a streak of 7 made shots in a row. Is this convincing evidence of streakiness, or could it have occurred simply by chance? Assuming this player makes 48% of his shots and the result of a shot doesn't depend on the previous shot, how likely is it for the player to have a streak of 7 or more shots in a row? So we want to do a simulation for this. Okay, so we're going to list out each of these 4 steps. So step 1, state. What is the probability that the player will make 7 or more shots in a row? Plan. We need to use a way to come up with the simulation. So we're going to do a random number generator. So we are going to let 1 and 48 denote shots that are made, and 49 through 100 denote shots that are missed, because it says, assuming the player makes 48% of his shots. Okay, use a random number generator with 1 to 100. Select numbers until you get something between 49 and 100. Record the amount of trials needed before getting a number between 49 and 100. Okay, it says do 30 repetitions and create a dot plot. So it would look like, let me pull up a random number generator. Random number generator. Here is the example. So you're going to generate, okay, 25. So he made. Oh my gosh, this is crazy. Okay, he didn't make. So that was 5. We went through 5 trials where he got 5 in a row. Okay, so that was one. Now let's do it again. He didn't make. So it was 0. All right, we got 1 shot made. Oh, he didn't make, so that's 1. All right, 0. Okay, he made 1. Oh, he didn't make it again, so that's 1. He didn't make it. Okay, he made 1. He made 2. Oh, that's it. He got 2. So you're going through and counting up how many trials and getting the data from that. So let me close this. All right, so do 30 repetitions and create a dot plot. So these are the number of shots made before a miss. So this is the do part. So you create some kind of way to collect and record the data. And then conclude, use results of the simulation to answer the question. So remember the question is, what is the probability that the player will make 7 or more shots in a row? 1, 2, 3, 4, 5, 6. I think it went 0. 0, 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5, 6. So this is the 7. So in our simulation, we got nothing. So none. So in 0 out of the 30 trials, the player have a streak of 7 or more shots. We would predict that there is approximately 0% chance of the player having a streak of 7 or more shots. So that means that the player is streaky. Once he makes 1, he kind of gets on a roll. Okay, so that's how we would do that simulation. Okay, let's go to the next one. Stratified sampling. So suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper and mix it up into a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggests that I should stratify by class, meaning I take and separate the 2 bags, okay? Put seniors in one, juniors in the other. But we have already mixed them up. But we agree that we would appropriate to select 4 seniors and 2 juniors. However, since I already mixed up the names, I don't want to separate them all again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names, i.e., I may get 2 juniors before I get 4 seniors. So design and carry out a simulation using Table D. It's a random number table to estimate the probability that you must draw 8 or more names to get 4 seniors and 2 juniors. Okay, so let's go through the steps. Step 1, state. What is the probability that it takes 8 or more selections? So we get that directly from the question. What is the probability that it takes 8 or more selections to get 4 seniors and 2 juniors? That's what we're wanting to find. Plan. So it does tell us that we are going to use Table D. And we're just going to look at snippets of Table D right now. Label the seniors, so 0, 1 to 60, and 30 juniors, 61 to 90. Numbers 0, 0, and 91 to 99 will be skipped. Read 2 digits at a time until 4 different numbers, 0, 1 through 60, and 2 different numbers, 61 to 90. Ignore repeated numbers and record how many different numbers from 0 to 90 we looked at. So you have to name what each represents. So we wanted 60 seniors, so we went 1 to 60, but it has to be 2 digits. So that's why we did 0 to 1. And then we want 30, so 30 juniors. So 61 to 90 gives us our 30. And then you have to decide what you're going to do with anything that's outside of the numbers that we've already labeled. Okay, so that's why we say we don't look at repeats and we ignore these numbers. And we want to find out how many trials. So we're looking at 8 or more selections. So that's the trials. Okay, so we're going to read the table and record results. So remember, these are seniors, these are juniors. So 0-3 is a senior. 8-0 is a junior. So right now I have 1 and 1. And then I have to read across the line. So 22 is a senior. 93 I'm ignoring, so I don't even include that in my trials. 41, senior. So I have 1, 2, 3. And remember, we want 4 seniors, 2 juniors. And I go, so I got my seniors. All right. Oh, that's a senior, but that's a trial that I'm not going to include. 48, that's a senior trial I'm not going to include. 01, also a senior. 98, I ignore. 77 is a junior. So now I have everything I need. I have 1, 2, 3, 4 seniors and 2 juniors. So we've got to count up how many trials we went through. 1, 2, 3. We ignore this one. 4, 5. We have to include this one because that's a trial that gave us a senior, but we didn't want a senior. 6, 7, 8. We ignore the 98. So 9. So that would go right here at this green dot. Number of different numbers needed to get 4 seniors and 2 juniors. So then this would be repeated, okay? Using different rows of the table for more trials. Each dot represents a result of one trial. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were 10 different trials on this one. All right, so we want to answer the question. The question was, what's the probability it takes 8 or more selections to get 4 seniors, 2 juniors? So here's our 8 or more. So we count them up. It said in this simulation, 8 out of the 10 trials, so see how there's 8 here, 2 are outside, were required for a selection of 8 or more numbers to choose 4 seniors and 2 juniors. The probability it takes 8 or more selections is approximately 80%. So 80% of the time. So that is our conclusion. Okay, so using table D, that random digit table, we've got to make sure we address some common errors. So one of the common errors is labels. You have to make sure they are the same length. So it says labels, not the same length. So you need to say 0, 1 to 50 instead of 1 to 50. You have to use the 2 digits, okay? Same length. And then not mentioning with or without replacement. So you have to address ignoring repeats or not. Okay, you have to cover all your bases whenever you're writing this out. So it's very clear, very concise language. The reader should not have to guess anything because remember, they have to act like they know nothing. Okay, that is it for our section.